Okay, we continue. What is the program?
So, next speaker is Jorge Bertueta and Carlos.
Yes.
Yeah.
But you had already one. This is the second one?
Yes,
Yeah.
I will just present an introduction, and then Jorge will speak most of the part of this talk.
Tell me the program in a moment, because I am lost. Okay, yes. Okay.
Are missing some people.
Yes. Let's wait for everybody else to come. Where is one you and one you is here?
Yeah.
He was not?
Yeah.
You have his phone number?
This is your time?
Yeah. I don't have his phone number.
No, I have the beach.
Yes, can you call him? We have to wait. We cannot do without him. And what is missing? Gregory.
It's there.
Oh, you're here.
You've got mail.
L'hai letto questo articolo di cosa hanno trovato?
La soluzione esatta, cioè che non è il campo magnetico, non è test.
Quindi è un campo magnetico per Newman allineato.
Kerr, no?
Che è allineato.
Sempre allineato. Infatti stavo facendo i calcoli dell'espansione, per tenere ordine, il secondo ordine in campo magnetico per vedere se si recupera era la soluzione di Ward. La soluzione di Ward deve essere ordine zero.
Ma anche la nostra soluzione della carica indotta.
Se con quella di Ward sì, a ordine zero sì. Poi c'è il primo contributo, mi sembra che sia B quadro, però sto verificando.
Ma la cosa interessantissima sarebbe vedere cosa succede alla carica indotta.
I campi che usiamo noi penso che non ci sia differenza, perché in unità geometriche i campi magnetici nostri sono 10 alla meno 10 m alla meno 1.
Sì.
Quindi, sto facendo per verificare l'ordine appunto nella espansione in serie, però è
Vado subito, è importante, ma soprattutto per la carica indotta.
sì, verrà analogo, qualche espressione analoga, infatti stavo facendo i conti.
What happened to you managed to
He didn't respond to the call.
did you send the message?
Yes.
Did you answer? No, not yet. Good. Well, it's fascinating that progress can you imagine that this solution just arrived yesterday. The solution incredible that in a few minutes, within a few hours, it's oh here you are. Okay, we can start. Eh? We can start.
Okay, so let's start the afternoon session. Continuing with the RRR model about dark matter fermions. These are some developments regarding supermassive black hole formation and the consequent applications. So I started.
Just for my curiosity, in this image, the dark matter component is tangent to the baryon. In the one you show us this morning, it was below the baryon. Or am I wrong?
No, Prof. The baryon here is dashed green.
But here they are red, no, the baryon.
You mean almost touching?
Yes.
The confusion.
The one of this morning,
Yes, I
they
understand.
were very separate.
Yes, the difference is in the log, which is in the logarithmic scale, makes it's an impression that is touching because it's in logarithmic scale. When you put in linear scale, you really see a larger difference.
Like this morning.
Like this morning. So both are compatible, but this is in log scale, and then everything is more compressed. But it's just a numerical.
Just to understand.
Yeah.
But anyway, from this morning, if you take the Gaia data for baryon, they are well above the dark matter.
Exactly. Yeah.
But I was under the impression that asymptotically, that the dark matter was going down faster, and asymptotically, the dark matter was becoming dominant.
Yeah, the point is that the Gaia data already show the fall off in velocity very early in radii.
Yes, but this is the reason I'm asking. I was expecting that
More flat, you mean?
the more flat due to the dark matter.
No, yeah, I know, but it is not, if not the case. It's only when you sum up the disk plus the disk contribution plus the dark matter that gives a slightly flat part, but then start to fall off. So in the end, the flat part of the rotation curve in the Milky Way is only in a narrow window of radii.
Well, of course, we are speaking about the liquid.
Yeah.
So,
Let's say,
This is the thing I was asking.
Yeah. so,
If there is a very end and finally the dark matter comes out or not, this was my question.
yeah.
And in the Milky Way.
So only comes out after 10 kiloparsec.
Yes,
Because here, as you said, there is a flat regime
yes,
which is not governed mainly by dark matter. And then after start to be governed slightly by dark matter, then follow.
yes, but the one which we care is the one that not the dashed, but the other one.
Yes, the black.
Yes.
Yes.
And that one, my question is coming out or not?
Yes, it's coming out here. Start to go above the dash at 10 kiloparsec roughly. Start to exceed the green at 10. The contribution of dark matter.
Therefore, the dark matter continue at the end comes out or not?
Comes out, what do you mean?
Is more important than the baryonic?
Exactly here you can see this. When the black exceeds the green, because green falls down.
Here is this,
Green is the disk, the barrier,
yes.
and black is dark.
And what is the red that
The red is the total sum of the component. Total B squared total is sum of B squared bulge plus B squared disk plus B squared dark matter. So these are showing the contribution of each component. The sum is the red.
okay, I would like to see that more.
Yeah.
This is an important point.
So, well, this is
Write down this, that we will.
the equation. Maybe we.
No, the question, no, write down the red, the green, and.
Here are there are the labels.
Yes, but I mean, it's,
It's a lot.
let's go back to that one with the right. This is there should be a statement on this.
Yeah. Okay, so this is just to recall that there exists a critical solution, which is the continuous black, which the mass acquires the critical value of collapse. So this goes to the strong statement that dense fermion core can collapse into a supermassive black hole while still surrounded by a dark matter halo. Oh, this came badly printed. I'm sorry. This is a paper. Okay, this is on the growth of supermassive black hole from the gravitational collapse of fermionic dark matter cores. This is 2023, but this is the slide, the important slide. So this is the paper. So for say gravitating systems which surpass the critical mass, the one that also shown before Gregory, 0.38 Planck cube over fermion square, the core collapses into a black hole surrounded by a halo. And this fact is what I also were commenting to Professor Ruppini before, that when you calculate the sequence of equilibrium solution along a stability track, you can find these red, blue, and yellow correspond to solutions at the last stable configuration of the system. So this is to show explicitly that the core here, you can demonstrate that correspond to the turning point criteria in the density versus mass, while you have the surrounding halo, which is also critical, right? Because the solution is only one solution with the two regimes. And the interesting point of this is that therefore, in this example of 100 keV, this is an example of particle mass of 100 keV, you have a critical mass of 10 to 7 solar masses with the halo astrophysical, meaning we have checked in these solutions that the halo corresponds or respect the dark matter surface density relation, meaning the size of the halo and the plateau density are in agreement with observables of this scale of Galileo. Okay, so this is to show that not only, I mean, you of course carry the core, what happened with the mass, the critical mass, but also have an information about the size of the density of the halo. Now the question is, how does, because this is the last time configuration, which is a possible solution within the theory, perfect, but how does this dark matter core reach the point of gravitational collapse? How long does it take to reach that point? And are those conditions attainable in astrophysical and cosmological simulation? So this goes to the other paper, of baryon-induced collapse of dark matter cores. This is the, here is cited. Yes, so this comes to the next work we have done with baryon-induced collapse of dark matter cores into supermassive black holes, which goes to this kind of plot. So in this plot, we have done the following. We have solved the equation of segregated of fermions fully degenerate, so we only care in the core, and we put together baryons. So baryons are considered, regarding the total pressure of the system, is only governed by the degeneracy pressure of the fermion. So we neglect the pressure of baryons when entering the core and just account for the baryonic density. This time dependent on the baryonic density is considered through the hypothesis of Bondi accretion, this rho B, in these early stages. And so we, in the picture of the left, you can see two examples. The light gray line corresponds to dark matter plus baryon equilibrium configurations for this 100 keV particle mass, without, in this extreme case, without baryons at all, right? So it's a standard sequence of equilibrium configuration until the turning point in the maximum. Then we consider other possible series of equilibrium configurations for where baryons budget are more important, up to the case 0.8, just as the largest we consider. And so the interesting, let's say, interpretation of the figure is when you start, for example, at the beginning of the dashed line, without baryons, eta 0, then you start to capture baryons, so the dashed line with the arrow indicates the sequence of equilibrium configuration where baryons are starting to enter in the core due to the Bondi formula. And so it shows how the equilibrium configuration moves along this turning point diagram. And of course, at some point, we'll reach the red line, which corresponds to the secular instability limit for gravitational collapse. This is an expression, and this is encapsulate the different black hole masses, or the different critical masses, with the effect of baryons. So you have the traditional Oppenheimer-Volkoff approximation for full degeneracy, but depending, if you have 0 in a baryon fraction, you have the traditional MOV, though if you have some budget of baryons, you will have a modification of the critical mass due to baryons. As we have done with Professor Rupi, the tradition, and with Jorge, of course, the traditional calculation of Stoner or Chandrasekhar, this limit, this calculation of special relativity together with Newtonian gravity. This was also obtained here, but fully relativistic in this case. This is just to say that the dark matter collapse, dark matter mass, when accounting for baryons, is lower than the collapse, the critical mass of collapse without baryons. This we knew already from the Stoner and Chandrasekhar way of doing, qualitatively speaking, but numerically the per factor here is fully or more self-consistently calculated, because this is full GR calculation. Okay, so consequence of this is when you have baryons, you have a lower critical mass of collapse by this 0.2 factor. Once you have the collapse after accreting baryons, you can ask during this stage, you can ask how much grow the original mass, the original seed, and which time it took. So this is shown in this plot, in this example here. And for example, for a baryon budget, this is represented with Q, which is density over sigma Q. The mass of the central object start to grow until it reaches the collapse. But the interesting point is that it does in a fraction of giga-year. This is an example. This is in time instead of redshift. Jorge will show more examples with redshift. So here at this example, in 0.2 giga-year, you collapse from 3 10 to 7 up to 4 10 to 7, where for example, there are observed, James Webb has observed these high redshift obscure quasars. And for example, there is another example when you started from a lower seed, meaning, and then accrete baryons at a different ratio, and ended in 3 times 10 to 7. So this is again, this is also for what you and Remo, just to recall these results, because it's very similar what you have done. Though this case is before because you started with the black hole. Here we start with the core and capture baryons until it collapses to the black hole. And then of course the subsequent growth that we have also, and I would like you guys to check the 2023 paper. I don't know if you knew this, the black hole growth, on the growth of supermassive black hole. Yes, good, because in this case it's very similar what you have done. So yeah, just to have into account.
Which paper?
The 2023 that you also co-author is this one, unfortunately came a bit bad in the slide. Monthly Notice 2023. This was a collaboration because we did many things here. Is growth with an accretion disk once the black hole was formed, and we also obtained always sub-Eddington accretion rate and sub-giga-year time of collapse. But this case, we end up in 10 to 9, 10 to 10. This was to show that you can form 10 to 9, 10 to 10 supermassive black holes very fast from heavy seed. Instead, you show also that you can have the case of little red dot as well. Okay, so this was just to remember, and okay, and then I moved to the, because this was the introduction to Jorge, where I will show very fast one example. I need a PDF, but maybe I need.
Just one comment. I
Yeah.
didn't consider the disk because from observation of little red dots, people think that there is no disk.
Ah,
Entry says there's no disk.
yes, I see. Yes, that's why in value-induced collapse we consider.
Precise.
Can I have the help of the system manager for a second? Because I need a PDF which is here, but I don't see. I need to open a PDF. Is this one?
So what's the signature of it?
Double click.
Sì, perché non voleva.
I guess that's I don't think I've been
Exactly, it's my question.
can see it geometric.
Yeah, exactly.
Yes, and therefore this is, I will conclude with this comment that after Jorge's intervention, that this paper we published this month in PRD, where, because this is the next question, right? Once you form the black hole, what happens with the dark matter in the surroundings? Because of course you cannot extrapolate the halo all the way to the center. There is a theory of what is called dark matter spikes, which is how dark matter adiabatically grows in time, the surrounding density, until it reaches a steady state. This we generalized the Gondola and Silk work in the 90s, and I will show that this plot. I would like to show this plot on the left. Maybe a bit zoom here. Yes, yes. So in this plot here on the right, the sequence is the following. We started in the black core halo solution. We started with the traditional fermionic core halo. Then in this dash black there. Yeah, thank you. Where here. Great. Yeah, we started with this solution, core halo. Then this is for example of 300 keV. In stage 1, the central core, which is dash gray, adiabatically grows, as I showed before, and accrete baryons until it reaches the mass of the gravitational collapse. And then it ends in this dash dot gray, which is this one, because it grew in density due to baryons, and then it ended in this more compact configuration. Then at that point, it triggers the collapse due to the baryon-induced collapse that I showed before. Then, rapidly the particles reaccommodate under the central potential, because now you have where was the core, now there is a black hole. The surrounding dark matter accommodates, and you can calculate the new distribution function of particles around that. And after the collapse, the black hole is formed, and the remaining dark matter form a spike density, because consider when it collapses, there is no more this core. This is no more, because now you have a black hole. And this new or stage 2 case is where dark matter reaccommodated in a given time span, and this is the final solution. Therefore, after the black hole form, the halo is this solution. These are the solutions you have to consider, and you cannot. This is just to contrast with the case that you cannot extrapolate this like this. You need to consider the cell-consistent spike. Okay, and this is, I leave Jorge, where there are a lot of possible applications that you can consider when you have a black hole surrounded by these spikes, because it affects orbits, it affects Chandrasekhar drag, and well, many other effects that Jorge will tell. Thank you.
Okay. So, upload my PDF.
Está abajo, exacto ahí.
Okay, so I continue at this point. So I can jump some of the slides. This is just the theoretical framework that you know already very well, so I don't need to analyze some of the main results from this. Not all, but some of the most important for this thing. Carlos already recalled the Milky Way, and this is something important from what I am going to speak. This is our work in 2019. Where we extended this the analysis that we did for the Milky Way, but exploring the parameter space of the model to apply it to different types of galaxies. So from elliptical, ellipticals, dwarfs, and all the way up to clusters of galaxies. So we have this behavior, and this is an important plot, the one on the left here. So this is the total mass as a function of the core. Mass, actually in the literature, instead of core, you can imagine it's written mass of the black hole in the literature. And then there is a band here. This band that you see here is the so-called Ferrarese relation from 2002. Is the region populated by galaxies. So it's the mass of the galaxy as a function of the mass of the dark compact object at the center of galaxies. And we show already in this paper that our solutions cover that region of observation. So why is this important? The important point, and that band is fitted by this kind of law. So our model satisfies that relation between the halo mass and the core mass. What is the point here? The point is as when you showed this morning, for example, the halo mass function, so the density of halos for at a given redshift at a given halo mass. We are interested in our theory not only to show that you can form a supermassive black hole from the collapse of the dark matter core, that we already showed last year. But one important question is to estimate how many of these objects can you form in a cosmological setup. So, in other words, we want to estimate what would be the supermassive black hole mass function predicted by this model. So, to do that, you need the number density of halos that you can form at a given redshift as a function of the mass of the halo. In other words, what you showed when you this morning. But you also need a relation between the halo mass and the core mass. If you do that, you will be able to transform the number density of halos of a given halo mass into a number density of cores of given core mass. And then, by applying the theory of baryon-induced collapse, you can then derive a number density of black hole masses of a given mass. And that would be the supermassive black hole mass function derived inferred from this theory. So this is, for the moment, I'm going to show just some application of this kind of algorithm to compute that, of course, with some, word of caution, because it's ongoing work, and
we can, there are some approximation assumptions that can be relaxed, can be extended, can be generalized. But it's a first approach to show how we can do it and how can we approach the problem. Because it's not only, as I just mentioned, to show that we can form, but you have to form the right amount of objects. So, well, this was already recalled this morning. So this is what Carlos showed. So we are interested also in going into this kind of works of this kind of result of showing that the mass of the core, the mass of the black hole that you form, and as a function in this case is a stellar mass, or a halo mass will be a number bigger than this, by roughly order 10. And how do you can populate this diagram? Yeah, in this from this theory. This is one of the questions. And we will use what just Carlos recalled, so I will not recall that. The important point here is that this, to do that, you have to recall that this is a time delay distribution. You form a core of a given mass at some redshift, it will collapse and form a black hole at another redshift, lower redshift than the initial one. And so you have to take that into account when computing this supermassive black hole function. So you need to know from a given initial mass of the core at a given initial redshift from this theory, depending on the amount of baryons, from the environment of baryons, then we will contribute to massive black holes at some other redshift. So how to do that? We have to take into account this, the critical mass Carlos already showed, depending on the mass of the fermion and depending on this is the initial mass of the dark matter core in units of the critical mass of a pure dark matter core. So the Oppenheimer-Volkoff critical mass, I say. So this is the initial mass of the dark matter core, and so we have this kind of relation that comes out from our paper of last year. So we have to combine somehow this information. So the important, just jump this, is an example from our paper where this theory could be relevant, but I'm interested right now in telling this story here. This is how the mass of the core evolves as a function of time, and how it can reach the critical mass value appropriate for the initial mass of the dark matter core, because it did not collapse to any mass, but the theory predicts a very specific mass at which this core can collapse by accreting matter. So this was as a function of time in your paper, but we have to give this as a function of redshift. One of the important parameters here is not only the initial mass of the core, but also we have to define the properties of the baryon or the baryonic matter. So in this setup that was already recalled by Wang Yu this morning, using some Bondi accretion, and also Carlos just recalled it, the important parameter is the fraction between the density and the baryonic and the gas velocity q. This rho over v cube that appears from that formula that we encoded into this. This is a parameter that we call q. So everything depends on the initial mass of the dark matter core, the redshift at which it starts to accrete, and the value of this q. That gives you, that tells you at which redshift this object is going to collapse, and at which mass. So this is the setup. This is how it's an example how it evolves with redshift. The plot on the left is from our paper of last year. So the relation with redshift was somehow, it was implicit, it was not explicit, but there was a specific example of starting at some redshift Z0 that you see here, that's not there, and that it collapses at some other redshift 4 or 6 or whatever. This is more explicit now. For example, if you start with a core at redshift 15 or a redshift 10, you see the red and the blue. So we start to accrete, and at some point, it reaches the critical mass. You see, this is for a fixed initial mass of the core and fixed mass, for example, 100 keV of the fermion. So the critical mass is fixed. You see, in this kind of if I fix the initial mass of the core and the mass of the particle, I fix the critical mass. So what I can do starting from the same mass is just I move the initial redshift, and as a function of the initial redshift, you see the collapse is reached at a different redshift in one case and in another case. And so when I take a picture of the universe and count the black holes that I see at some redshift, I have to take into account in my theoretical derivation that the objects that contribute to that redshift are some very specific. Sorry, this is 0.1 in units where rho is taking up 1 solar mass per parsec cube, and the velocity in units of 100 kilometers per second. Yes. Yes.
Sorry,
Yes.
can I make a comment? I forgot, I need to make a comment in my slide which I forgot. The value is not chosen randomly, was chosen by two different points. For example, we consider cosmological high-level simulation, which with high resolution, to see how baryons accumulate around a central object. So we infer this value from a paper, and also
Cosmological.
no,
What kind of object? You mean they don't resolve this?
no, but
No.
the assuming high resolution is the closest we can get. Assuming.
Okay, this is precisely what I wanted to talk about you, but maybe I'll.
I know we expert in high resolution, which I
Because the resolution is not high enough.
You know the problem,
Yeah.
yes. I'm sorry, Oren, but this is really important point. So let me tell you I'm not expert at all, but I read the literature and my understanding is the following. There is very lot of difference in the accretion rate depending on the size. On the same object, keep in mind, on the same, so of course, I was just interested because we looked at this stability limit. We found that 10 minus 8 solar mass per year. But this accretion rate is on the central object inside the Milky Way in the very inner part. If you go a little bit further, you get 10 to minus 3, 5 orders of magnitude larger. Okay, on the same object.
Yes.
5 orders larger. So why this comes out? Because the matter is not falling into the central object. It is accreting, but it's accumulating, but it's not going in. So this is my question. You assume something, but how is this related to the accretion rate in different sizes? Because it might be that you actually have very high accretion rate,
Yes.
but nothing is falling
Yes,
inside.
of course, this is estimated in this kind of approach. It's estimated when you say it's at the gravitational capture radius for that velocity and for that density, and you don't know what happened next. On that radius of the Milky Way to segregate to sediment and
This is very weird architecture.
Uh-huh.
This for me.
That's-
You need to know all the hydrodynamics, but now you are saying if you use cosmological theory, you don't resolve it.
No, you don't resolve. But you can have. There is a typical numbers also if you take at the Milky Way, typical numbers of the density, velocity, and this is the best we can do at this moment. In fact, I don't want to force very much this. That's exactly why here we're showing with this parameter as a free parameter that as you move this a little bit, you see the changes and what you can infer from the number of objects per unit volume. I will show a plot, in fact. So we're not fixing that value, but we expect to get some information from the comparing with the data. The important point here is that this is a delayed time distribution. This is the important point to show here. So this is the algorithm. How you can do that? So you start with a halo mass function. I already mentioned that. Then you relation between halo mass and core mass. Then you transform that halo mass function into a core mass function. And you, by the baryon-induced collapse, you transform it into a supermassive black hole mass function using the fact that this is a delayed time distribution. And then, of course, that black hole that you fall continue to accrete eventually and grow. So you have also to account, take that into account when you do that. So this is an example just to show you. This is the halo mass function. It's the same that you, similar to the one you showed this morning. This comes from the paper in 2021. You see the PhD thesis of Raphael Yunis simulations with class form that they were shown, in fact, that for fermion masses larger than 10 keV is essentially the same as lambda CDM. Halo mass function. This is for different redshift. So you have the number density of halos of some given mass, and you can from this then with some relation that our model satisfies. Then you transform into a core mass function, and then with the collapse with the delay time distribution, you transform into something like this. This is the number of black holes of a given mass that you expect from this model. This is for a fixed value of this Q parameter. This is 0.1 as in our paper, and then this is a different redshift. How this evolves with the redshift, what you expect at, say, for example, 4, 6, 10, all starting, we are taking redshift 15 as the maximum one where we start the calculation at the inception of this course. So this is it's a pretty interesting number, this one, this density of the order of 10 to minus 4, 10 to minus 5 objects per cubic megaparsec. Because if you go to what is coming out from James Webb Space Telescope data, if I start to populate this redshift 4, 6, there's some data starting to populate this density of objects at this kind of values, between 10 to minus 4 and 10 to minus 5. We are currently verifying what is the best way to compare with the data. It's not clear at all, because also as Felix mentioned this morning, there are objects that are obscure, so there is an underestimation of the number of objects. And so we are exploring these values, but I can tell you right away that the numbers, these are in the order of magnitude of observations. So that's why this is interesting. I would like to show something more about this, and is, for example, what happens if you change the mass of the particle. The previous one was 100 keV. This is a comparison between 100 keV and 300 keV. So, of course, what 300 keV, you know, the critical mass for the black hole formation is smaller, and so you start to contribute to a lower mass. And so this is exactly what happened. These are two redshifts. The solid one is 4, a redshift 4, and the dash one is a redshift 6. Yes, exactly. I leave the same trend that you see here. This is the plot now. This was a fixed Q, 0.1. This is how they change. What happened if you change the Q? There are 3 values here: 1.1, a 0.01. Okay, different redshift: 4, 6, and 10. So, so the red color is Q1, blue color is Q.1. So it will be this one, and green color is 0.01. Okay, and the redshift are 4 solid, 6 dashed, and 10 dotted. Okay. So of course the mass of the particle is fixed at 100 keV in this case, as an example. And so you can see this red, these two, which are just these two. Okay, and so we can see the trend. And so you can see already here again the number of 10 to the minus 4, 10 to the minus 5, 10 to the minus 10, the redshift 10, which are the dotted one, is also very interesting because there are objects at redshift 10. There are upper limits on the number density of objects at redshift 10. They are more or less somewhere here, the upper limits. Again, I'm showing you how all these parameters change what is going on. There is something particular that I would like to show you that I forgot in the previous plot. I want this one. What is this one? Oh yes, yes. If you compare a redshift 4, for example, we have to compare the solid cubes. Okay, so if you fix, for example, the cube, so for example, let's see that the dash again the dash. So at the Q 0.1, this case, okay, you see a redshift 4. This peak of the red is higher than the peak of the blue. Okay, if you go to redshift 6, for example, to redshift 6, sorry, this was 4 Q 0.1. Let me see, 0.1 is blue. We were comparing redshift 4, so blue with the red. Wait a moment. Probably it's better to because there are too many Qs here. Sorry with the other. Yes, I think this maybe this is better. The point is that it's a change in the trend. There is a change at some redshift where some the number of objects they flips the density, the contribution flips at some redshift about 4. Apparently, the objects that contribute from some large Q and the number of objects that contribute to some lower Q is different. Start to populate different regions in this diagram. This is something that we are studying right now. So there are, of course, much work to be done yet. This was just an example of how we can do that somehow. We must know how the parameter Q, this density over velocity Q of baryonic matter, changes in different ambience, different galaxies, different redshift, etc. This is some information that we have to collect to make a better prediction. If the supermassive black hole fan motion can explain the outward shift of the Ferrarese relation, the relation between the core mass and the halo mass is expected to produce larger objects of larger masses at high redshift. Actually, the answer is yes. Yes. It's implicit in our calculation, but the answer is yes. We can constrain further the fermion mass from the supermassive black hole mass function at high redshift. As you saw, the answer is yes, because the number of objects that are predicted is very different, and also the masses at which they start to contribute. The other one, this is a curiosity, if we can obtain or the density profiles of dark matter by solving the Einstein equation with different boundary conditions and accounting for decrease of the background density. This is some exercise that we probably will have to do to see how the core, if we can infer directly from the theory the relation between the mass of the core and the mass of the halo as a function of redshift, for example. And then, in that way, this is what I mean, kind of obtain a Ferrarese relation to pure theory. And of course, there are more points that could arise from this. This was the first part I want to mention. So we are working in that direction, or looking at the predictions and comparing with the supermassive black hole mass function from high redshift observation of James Webb Space Telescope. So there are further astrophysical probes for the dark matter that we can use from this kind of work. One which is important in view of the forthcoming LISA, Taiji, and Tiankin space-based interferometers for gravitational wave detection. We can look at the difference, for example, between a supermassive black hole binary mergers and dark matter forced binary mergers. This is one possibility to put constraints on dark matter properties, and the detection rate depends critically on the supermassive black hole mass function. Where one point of the previous work is very relevant. There are these differences be detected in stochastic background within nanograph and European pulsar timing array. This is also something important related to the previous case, as this background is at least the idea is that is dominated by mergers of these kind of objects. The hypothesis is also 2 sigma right now. Where the dynamical friction effect, this is of this dark matter spike that Carlos showed around the supermassive black holes. From the case of dark matter collapse, so just in other words, the distribution, what is the effect of the redistribution of the dark matter when the core collapses, the dark matter redistributes around, and these new kind of profiles, which differs only in the vicinity of the relative vicinity of the supermassive black hole that you for can changes, for example, the dynamics of supermassive black hole, or for example, of mergers, and so on. So this is what, and the merger, this could it could be different, for example, in quasi-normal modes. Then there is also the dark matter dynamical friction in compact object binary. This is different topic. Has nothing to do with supermassive black holes. This I will show right now some result that comes from paper of 2017 and specify for the case of the double pulsar, because it's really asked yesterday. I just isolated the results yesterday night to show here. I will show you right now. What about intermediate black hole systems? They are also subject to dynamical friction. So this is something to be absolutely have to be evaluated. This is a curiosity. If Sagittarius star were a supermassive black hole, so a hypothesis, then it would have a dark matter spike, which would be very prominent. So how would be the effect on the S-cluster star orbits? And would this lead to another way of ruling out supermassive black hole nature for Sagittarius star? This would be it's a question. Then this is very interesting. After a supermassive black hole forms, it could accrete dark matter particles at a comparable rate of baryonic matter accretion. And this is something to be absolutely evaluated, because even if the dark matter is collisionless, and you expect a much lower accretion rate with respect to baryonic matter, but the density is much larger, and the black hole does not care if there are dark matter particles or baryonic particles. So this we have some very interesting results, but we are working. So and then this is well, if referencing millihertz gravitational waves. This is for Lisa, Tianqing, Jean. These mergers, these dark matter cores have compactness that you mentioned this morning of the order of 9m. And so the approach and the frequency of gravitational waves is different when you compare it with two massive black holes. So you expect somehow differences in the case. This is the sensitivity cube of Lisa, for example. And this is the approach to merger of two dark matter cores. And some parts, the final point, this is ended at the point of where the radius is of the order of twice the radius of the core, so that the 18m roughly. If you have a supermassive black hole, it will continue on the line, so at larger frequencies. So we are comparing the differences. So will be different also in redshift for detectability of this kind of objects. So its redshift can be even of the order of redshift 10. So it's quite promising detection. And quasi-normal modes, there will be also the difference if you have a pure Schwarzschild of the black hole with dark matter, and you will have different in the quasi-normal modes of the merger. So there are many things also in this thing, but I would like to go directly to this final part in the dynamical friction of compact object binaries. So when you have a binary of 2 neutron star or 2 white dwarf, or a neutron star and a white dwarf, for example, in the dark matter background, the dynamics can be modified relative to a dynamics in pure vacuum. You have to quantify what is this effect, because this effect is that was computed by Chandrasekhar in 1943 for clusters, for a subcluster, not for dark matter, can be applied also in this case. We can compute the dynamics of the binary under this drag force that is going to change the dynamics of a binary. But how much is the question? So we're going to go directly to the results, and what we want to compute is how much it modifies or it affects the decay rate of the orbit. This is the important parameter to be computed for the point of view at least of timing data of pulsars. So this is a plot from paper of 2017. These are the density of dark matter from our model for different particle masses, 48 keV is this one, and this is the 345 keV, and this is the Navarro-Frank-White profile. And this is what would happen at 0.1 kiloparsec. This is from the paper for 2 neutron stars of 1.3 plus 1.3 solar masses as a function of the orbital period. So we will see right now that a relevant period could be 0.1 days, for example. That is the period, orbital period of the double pulsar. Hughes-Taylor pulsar is 0.3, so it's more or less here. Okay? And at this point, you see the prediction for the contribution for dark matter frictions is to be low, 10 to minus 20. 10 to minus 20. The gravitational waves will be 10 to minus 12. So this could be apparently a big difference, apparently. This is the Navarro-Frank-White here already of the 1 order of magnitude larger because of this difference in density. Okay? But it's important to check, and this is the table from the paper. The first object was the double pulsar. See, it's J0739, 0737, sorry, this is the double pulsar, and this is the Hughes-Taylor pulsar here. So you can compare, this is the P dot contribution from dark matter friction from our model, and this is the compared to the gravitational waves. Of course, this is much smaller. But these objects, the distance, if you see here where they are located in the outskirts of the galaxy, where more or less here, where the density is very small.
Very interesting.
Yes,
Why
to the table.
So the last column is a calculation based on your
Yes, exactly. With the contribution of dark matter to the decay rate.
why the double pulsar system has a much less, or has the most stringent limit. No, there's also minus.
This is minus with respect to, for example, this is the double pulsar.
10 to the minus 21 power.
Yeah, this is the minus 12 gravitational waves.
Right, there's also a system at minus 1.5.
Which one? This one, for example. Oh yeah, these are a neutron star white dwarf system. These were at the time where we found data from the P dot. These are neutron star, and neutron star white dwarf, and there was also one white dwarf system, but we could find some.
That's the predicted effect. Not a sort of a derived constraint from the data.
No, yes, exactly. This is prediction. This is the prediction if order 10 to minus 20 for this pulsar. 10 to minus 20 for this object. What is interesting? I found very interesting this one. This is the table. This is the double pulsar parameter from the paper of Kramer and collaborators in 2021. So it is the most updated data for the double pulsar. What is interesting in that paper? That they say that already the effect of the emission from the pulsar A, the electromagnetic emission, is relevant for the calculation. But if you go and see what is the P dot from the spin down rate of the pulsar, so the electromagnetic emission is already 10 to minus 18. 10 to minus 18. And they say that it's relevant for the calculation. Because it's of the same order you see here, because it's at the last terms of the error. And so they take into account that into the analysis of the data.
The loss of, repeat again?
Is the loss of energy from just from a magnetic dipole.
Yes.
So the spin down rate. Since you have the spin down rate, you can make this computation.
Yes.
So from the speed, from the, let me see if I have it. I think I have it here. Yes. I don't know what is that. I don't know what is that. Okay, I estimated this to cross-check with Kramer paper. And in fact, I obtained this 2.3 10 to minus 7 times the moment of inertia of the pulsar in units of 10 to 45 grams per cube per centimeter square. And this is the value that they put in the paper, 2.3 10 to minus 7. So this is the contribution, how the loss of mass energy of the pulsar affects the decay rate of the orbital. Okay? So it's not far from the contribution of dark matter. If we speak about 10 to minus 20, or if you speak, what is the point now? I will show you what is the point.
Much less than the gravitational wave.
Exactly. 6 order of magnitude.
Same order of magnitude?
6 order of magnitude.
6?
Less.
Yes.
And they say that it's relevant.
It's relevant for what?
It's relevant for the analysis of the data.
Actually, there are 9.
Yes, exactly. This is the point.
They have accuracy up to 9 inches.
This is the point.
Amazing.
That the analysis that we got is the leading order is 10 to minus 12, but they have different decimals in the precision. So 10 to minus 17, for example, is somewhere here. And so it's at the limit of precision, but they are getting there. So what is...
You mean independently, that is more, if you, the significance of the term
Exactly.
is important.
The significance of the term is important.
And in principle, you could see if the change is mainly due to that one or not.
Yes. Yes. And then there is something that I think at least is interesting. It's interesting. So if they say that 10 to minus 17 could be already important, for example, there is enough data, we can ask, for example, what had to happen in this picture to go to this level? For a double pulsar-like system, it means that we have to increase the density. That matter friction, the drag is proportional to the density. Okay? So it's enough if you go to a region of the galaxy where you have 2 order of magnitude or 3 order of magnitude larger density, then you'll be already at the same level of the effect of pulsar emission. Okay? So for the Navarro-Frank-White phenomenological profile, that is this one, it could be at some 1000 parsec.
No less.
Somewhere here. Okay? So, and in our case, RAR model, 0.01, 0.1 parsec. So this is somehow prediction. Okay? A prediction. So we will find some double pulsar system, so a neutron star binary with good timing at this kind of distance of the galaxies, then that would be a very interesting and very promising system to put a constraint on the dark matter.
But in the case of the binary pulsar, we are very far.
We are far because it's here.
As far as this.
Yes. It's 0.1 kiloparsec. And the Hughes-Taylor pulsar is a 1 kiloparsec. This is here, and there here is the, yes, these are, yes, 1 kiloparsec. And 0.1. North cluster is here. Yes, S cluster is here. This cluster is here.
Well, sorry, one comment I think very relevant now. The nice thing, of course, if someone finds a binary pulsar inside 0.1 parsec, according to our theory, dark matter is the more relevant, not baryons.
No?
Not baryons, not the baryons, not the baryonic matter. Below 0.1, yes, exactly. And no, this is just to say that we don't have interference of baryons. It's a standard. We know the dark matter, so there is I mean, we know. Yeah, we predict that. So,
But these systems are so clean that you don't have many choices. You have gravitational wave to compete with electromagnetic emission and dark matter.
yeah.
But
Not
the
more than that.
interesting thing you are telling is that even our system is in a region in which dark matter can be important. This, I think, is a very important statement. Namely, that this is the key point. That even in this distribution, the dark matter at the distance of the halo is significant.
Yes. And maybe in some 2 or 3 years, if they continue to take data, maybe the NFW profile could be ruled out.
Yeah.
This phenomenological profile like this one could be ruled out
What do you do with that?
because it will contribute too much to the P dot in the double pulsar. If you continue to take data, they reach the level of 10 to minus 19 in P dot, then they can say something about the dark matter.
Namely, that it could be higher.
It could be, it depends on the result,
Yes,
the higher or lower.
they could check that.
They could check that.
But what I excuse me, just one moment, please, for the day with me. And from our curve, we emphasize always the code, and we did not emphasize
This region here.
yes, this.
This region
Well,
here could be already important.
We yes, and this is very important. Namely, we emphasize the core, but I did not care very much about how deep it goes down.
Because it's sharp, but not that sharp.
Excuse me?
It's sharp, but not that sharp, but not a delta. It's a continuous,
It's a continuous soft.
soft.
Yes.
soft,
Yes, it's not this is the interesting one.
Yeah.
Because there could be different reasons. Of course, it goes up again after.
the velocity goes up.
Excuse me?
The velocity goes up again, but it is
No,
density.
the density in our diagram, the average density. I can't remember. The density goes up again.
No, the
It
velocity.
stays, but not the density stays like that. And okay, but then the trick would be just to therefore what we are saying is that the trick is just to see the contribution. I mean, the asymptotic contribution gives that one. Is the question I was asking.
The asymptotic is the Galileo theory.
Yes, but it could be that this asymptotic is larger.
More extended.
No, not more extended, be larger than this one. and still comparable with the flat rotation curve. I mean, to see if you could have a density,
And still within the error bars.
eh?
And still within the error bars.
Yes.
This is what that is
I
the content.
know, but yes, but then there is another extremely strong outcome of the theory, which really is that. For example, let's assume we have another galaxy similar to the Milky Way with 4,026 at the center, but with much larger halo. So our theory, the largest
I
halo.
mean, what you are saying now is a different reason. Let's assume that the Small Magellan Cloud, which we know as a big black hole, we know lately, which it could have a dark matter component. I mean, we have to go back to the Magellanic Cloud. Because if the Magellanic Cloud start to have dark matter, let's look again the data of the Magellanic Cloud. I mean, what we know is that there is a big black hole, because we see the particle coming out and so forth. And how big is that black hole? 10 to the 5. Is similar to ours. Therefore, there could be the addition of the two 10 to the 5 black holes in the galaxy. You understand what I'm saying?
Mhm.
And if you increase that by the sun, maybe we are in the game. This is really completely, which I would really enjoy this for my personal reason. But I think that you are following. I hope this is new science.
Right.
We want to, I hope you follow. The point is, we know that in our galaxy, there is a dark matter of the order of 6. But it could be also a similar one in the Magellanic Cloud. And that one in the Magellanic Cloud will add the dark matter to our dark matter. You understand? We will have a similar curve in the Magellanic Cloud. Dark matter. And it would be interesting, but not so extreme. I think the Magellanic Cloud is the best case, because always there is the black hole in the nearby galaxy. But then we don't gain very much, because it's very similar to ours.
Probably the most
Right,
promising region is this one, very likely.
Excuse me?
The most promising region to detect these kind of things is this region
Yes.
here somewhere. There. We're very interested in that.
Yes, because Jorge maybe said that even if you consider LMC, hardly you will increase by orders of magnitude. Probably you will increase by a factor of 1.5 maybe.
This profile, for example, the purple one, with respect to this position, okay, it increases almost 5 orders of magnitude in that region. It means that 10 to the 5 bigger the effect on the P dot of a binder for this profile. For us, it's less. So that would be very interesting to find some object somewhere here. This is
Actually, Jorge, there are part of the light. Now they use generalized. They no longer use
Yes, none of them is in that region, unfortunately.
Someone knows observational capabilities. Why never observe any contamination of other? Why never?
I have to check why there are no more. There is also the problem of the called missing pulsar problem that they don't find. In fact,
There was alternative explanation, an inflation line right from the center. It should be pulsar origin. Pulsar generate electromotive wings, and these wings produce an inflation line. But the question is, if there are so many pulsars, why do we not see them?
Should not be made.
No, they say instead that should be many, which will explain an inflation line. And they see, there are some indications that there will be many.
Which inflation line? The one that yes, I understand. But, excuse me.
Oh, you asked, yeah.
Yes, but from the yes, from the data of Russian satellites. From the
It was detected by many satellites, in particular in the ground.
yes, and about the big emission of yes, the one we discussed with Sunyayev, and I thought it was HLB.
The eroded doesn't produce because it is soft X-ray, and the inflation line is 0.5 millimeters. Therefore, eroded is not significant.
I remember there is this point of a line of 0.5 millimeters from the galactic center,
And that is significant. But later detection was.
which has nothing to do with the data of and how this compares.
One interpretation is that this line comes from electron generated by pulsar magnetosphere. Yes. So there might be many pulsars inside the galactic system.
And none have been found. None.
But it shows there are no.
Not even one are observed.
There is a magnet.
no, there is a magnetar.
One magnet.
Yes, there is a magnetar. There is a magnetar somewhere here.
And can we say something about
But it's single.
this single?
No, I don't think it's that close. But
No, is that this is logarithmic plot actually. Yes, I think it's because this is the S cluster. This cluster is more or less here, and it's more or less a bit farther than the S
it's
cluster.
only 1,000. That magnet. I think.
Oh, let's say I think it was like 10 to minus 2 parsec or something like that.
Yeah, there is one.
Can I ask about the why the NFW in fact equivalent to I don't understand the text in the box. So why-
Okay, how I come to this conclusion? It's because the drag, the effect on P dot is proportional to the density of that.
right?
Uh,
The reason NFW more centrally peaked.
No, it's because this is this region here. So I'm just comparing the result for the double pulsar, which is here. The Navarro-Franken-White here will give roughly 4 order of magnitude bigger, or here 2 order of magnitude bigger effect. So we'll go already to the region of 10 to minus 17.
No, but okay, because it's double pulsar like.
Yes, double pulsar like. An object like a system like the double pulsar at this distance with the same feature.
No,
Or
but we are interested in that one. I'm interested in that one, in the real one, not in another one which goes there.
which we are still to see.
The point is we have one,
Yes, we have one.
and where it is in this plot.
Is here.
Exactly. Therefore, we have to see if we can increase the number of dark matter in that region. And there is a possibility from this nearby black hole, which is similar to ours, and is clearly of dark matter.
Yes, but let's assume that this large Magellanic
Yes.
cloud has a plateau density of the order of ours. Let's assume of the same order of
Exactly.
ours. Then, exactly. Then you will have a factor 2, but I guess it's not enough.
Well, it depends.
Yeah.
Let's see what we can do.
But it could be also just question of time. We continue to accumulate time with data, increasing the decimal, the accuracy of the measurement. For
And
binary pulsars is called everything. It's always question of time.
therefore, what you are saying is that what is important is the number of decimals.
Yes, in this case, yes, the number of decimals, the accuracy of the measurement. Bit by bit, you're adding decimals.
And that the delay due to dark matter could become similar to the one of gravitational wave.
Yeah, no, no.
To one of
Not similar to the gravitational waves. Similar to gravitational waves only in these regions of the galaxy. Not similar to the gravitational waves, but enough to be constrained by the data. High enough to be constrainable by the data.
similar to the electromagnetic.
Similar to the electromagnetic emission of the pulsar. Similar effect.
The gravitational wave will be similar to the electromagnetic radiation. I don't understand.
No. The contribution of the dark matter could be of the same order, or no, not the same order. Could be is large enough. I mean, let me contribute. In this region, dark matter is 10 to minus 20. Pulsar emission is 10 to minus 17. Gravitational waves is 10 to minus 12. Okay, that's a leading order. But they say that 10 to minus 17, that is the effect of the pulsar emission, okay, is already starting to be important for the data because of the accuracy of the how many decimals from 10 to 12, 10 to minus 12. So what I'm saying is that maybe with time, with enough time, the decimals will continue. They will continue to add decimals. Okay? And so in a few years, they could reach the accuracy of 10 to minus 20 or 10 to minus 19. The accuracy of the result. Not that the speed, the orbital decay will still be 10 to minus 12, but the accuracy will reach levels of 10 to minus 19. The accuracy of the orbital decay.
Yes, but you cannot reach the point that you can compare to the gravitational wave.
No, only in these regions. In these regions you can.
Therefore, the only possibility gravitational wave could be valid is if we are in the dark matter of our close to our
Yes.
If more close.
Yes, for example, in this case are 7-8 order of magnitude.
Yes.
Okay. Here the density is 10 to minus is 0.1, 0.1. I think this is between 0.1. So it's enough to go to 10 to 7, 10 to 8. Is this region?
No, 25. Because it's 10 to minus 2 the plateau.
10 to minus 2.
Yes. So,
10 to minus 2 plus 7 plus 8, 10 to 5. So you go here, is this region.
therefore the trick would be to increase the dark matter. Can we reach a possibility, put an upper limit of dark matter at the position of the line?
Oh, yes, 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 yes,
Yes.
yes, yes, it would be this order, 10 to minus 17. So this here is 10 to minus 20, means increasing 3 order of magnitude the density of dark matter. Would be from 10 to minus 2, 2 would be 0.1, the upper limit of the density of dark matter. 0.1 solar masses per cubic pascal.
Yes, already in point one you go above a Gaia tier 3. That's why it's important Gaia tier 3. Because before the full data were error bars were very large, you could expand much more. Now the game is much more stringent.
1
for density.
from 1 here. From 1. And here I was thinking if there's somewhere I take to this is 10 to 3 parts like more or less here. I was thinking it was
But
already
this,
ruled out by.
But excuse me,
I was thinking another stuff.
let's forget about the. Let's go back to that picture. In the other picture, we have in the other picture where we have the density of dark matter, okay? With the baryon.
Okay. You want I put it? I put it.
Excuse
Do you
me.
want to
Yes.
see that with the baryonic?
Yes. And what I'm saying,
Yes.
yes. Therefore, the point is that we have a spike in the density.
Now this upper is velocity. Upper is velocity.
Excuse me, you answer. Okay. The important point is not the velocity, but the one below. And now the trick is to see if we could increase. Let's be crude. How much we should increase that density?
Okay, can I give you an answer based on this? Because in our paper of 2018, this one, okay, we've used the effect of the increasing density of the dark matter because of the change of the particle mass to put limits on the particle mass. So if you see, for example, the yellow, okay, and the region of the double pulsar is here. So the yellow is I don't know how much about the black.
Maybe 1/4 of magnitude.
Maybe half or 1 order of magnitude, and this yellow one is already I don't know if
Or
at this
changing the
distance.
mass of the particle instead of.
But increase, but because no, I'm taking the value of the density here produces an effect of the velocity on the velocity that is already could go is more stringent the rotation curve than the pulsar. This is what I mean. I mean, if you increase the density of dark matter here at this position by 1 order of magnitude, it will be already ruled out by rotation curve data.
Yes, depending on the mass of the dark matter.
Yeah.
Yes, exactly. I mean, taking
into account
taking the higher masses.
No, the lower mass.
Lower are ruled out.
Not the lower are ruled out, but if you take 100 kV to 100, it will be close to this black.
No, I would like to take 40.
40 will be again they collapse here. I mean, they are the same, have same density here.
And what is the yellow line?
This yellow is I think it's 0.6 kV.
0.6.
0.6 kV.
This was, I remember, when we did first this plot, we did more hertz. Between 0.6, we did something like 10 kV. But the referee said, put a very extreme case where it's clearly ruled out, because 0.6 is clearly ruled out. But the 10 kV is, for example, 8 kV, 7 kV is also ruled out. Slightly, but ruled out.
What I'm trying to say is that the position of the double pulsar is here, okay?
Yes.
The yellow one has this density above, okay? If you go vertical, they have the same scalar. The contribution to the rotation curve will be here, but the data is here, you see? So at this position, the density of dark matter, okay, cannot be that bigger. Only one order of magnitude would be already ruled out by rotation curve data. So it's more, in other words, it's more stringent, the rotation curve data than the double pulsar data to rule out dark matter density, to constrain dark matter.
Unfortunately, you have to wait to find some binary inside the central parts. Otherwise, I don't see any for the dark matter to compete with the other effects.
What's the binary inside?
Yes, a pulsar, a binary pulsar inside the central part.
Yes, of course, but we are not interested in that one. And if you have a binary pulsar with the different characteristics, of course, but we are interested in that one. Okay, we have to keep thinking.
Yeah, we have to think. This is only from timing, but we're making also what would be the precision with the LISA, TAIG, data for phase-based interferometers for binary pulsars. The accuracy could be large enough to also say something.
It's up to which year? 2030, 2035, 37.
But we're interested in that one.
No, but yes, but they these are targets. This binary. They can see to this. They can see to this binary with a lot of data.
Very, very interesting.
Now we can go for tea break.
Sorry for the.
I cut you off.
No? We can go for tea break and I think we would have 10 minutes.
I like your speed, your T speed.
Yeah, the question.
For the NFW, for the NFW profile, why so I still quite get what's the why 100 parsec out?
100 parsec, yes.
So for assuming that you can play a double pulsar at 100 parsecs.
No, the double pulsar is at
1 parsec.
let me go to the data is
Just in that.
oh sorry, it's 1 kiloparsec.
1 kilo.
1 kiloparsec is the double pulsar.
So, but you place the double pulsar at 0.1 parsec
Yes,
to the galactic center,
yes.
you can see measurable effect.
Yeah,
And so what does the last statement?
this is I mean, if you take this, this is from fermionic dark matter, okay? So to reach the level of 10 to minus 17, you should place that system. You should place that system somewhere here, okay, to get this level. But the NFW, you see, it has a much drastic slope here. So if you to reach the 10 to minus 17 level, it's enough that you go from here to here. So to here.
Right, so I guess the slope you guys are considering is even more centrally peaked than NFW.
That's right.
Below 0.1 parsec.
Below 0.1 parsec.
Or 1 parsec.
And this is the reason why we are considering where the Magellanic Cloud, where there is a black hole similar to ours, to our, the dark matter.
How well do we know the rotation curve of large magnetic cloud?
Well, we know very little indirectly because we see a junction of high velocity object in time that there is a large black hole. but we don't have enough data.
Yeah, this is a good question. To the halo of the LMC is not much data. To the halo, to the black hole, yes, but to the halo.
If we have a
It's
black
not
hole,
covered by Gaia.
Yes, yes.
Yes, but I don't know
Yes.
how much they could detect each star inside to differentiate from the host.
There's even, I even used but I didn't do it myself, I even used a paper that update the proper motion of M31 using Gaia result.
Okay.
So it's some average of the.
Yes, definitely we have to check the last Gaia data of LMC. Definitely, I'm not sure what is the.
Yeah, another constraint is the H1 images. So because you get the authorship H1,
Ah, yes.
but it's broad, so sort of do some average.
So full data uses H1 hydrogen, ionized hydrogen. But
but the novelty is that another large black hole would have a halo large of that matter. And therefore, if there are more halo of that matter in the galaxy, that is tremendously important.
So another,
Or binaries between 0.1 and 10 parsec, they would be very interesting.
Yes, but that is independent.
That would be easier.
But what we are interested in is, since the real observational data, real observational data of gravitational wave, there are three. Only three. One is the 17 whatever. The other one is the one done by injection. And then the binary pulsar. There are only three. If the binary pulsar, which is by far the best, is put in jeopardy by the dark matter, and it's incredible. Only three. Two certainly fake. One absolutely valid. But let's see if we took everything into account.
let me just be wild here. So another thought experiment we can do is, suppose we find large number of fast radio burst cores behind the large magnetic cloud. Then behind large magnetic cloud,
Yes.
then we can do gravitational lensing
Yes. Of course. And then
analysis
I fully agree.
yeah,
I fully agree.
and
And
determine the halo structure depends on where you have.
one promising thing is that typically smaller halos has larger plateau densities. This is typical.
where
When you do analysis of many galaxies, the Donato relation. So
Yes.
smaller halos have larger plateau density. Smaller sizes have larger plateau. So if LMC is somewhat smaller, which it is, maybe we can arrive at, but I would say no more than 1 order of magnitude above. I
you
estimate
mean the average density of the plateau is higher.
for smaller size.
Why you would have a smaller size thing?
Because LMC is smaller than because it's a satellite.
Yes, mass, but
Yes.
we don't need.
The size
know-
as well. Size has-
We don't know the. But anyway, I think it's extremely worthwhile, interesting topic. Maybe we should highlight, write something about because it's really important. I mean, I hope you understand the key point. I mean, we know that two sources are fake. The third one is where everything relies. Now I understand why Alfred is very much concerned about the work of, I was telling you yesterday, about the work of Cameron. No, I understand. It's very, very, very concerned. Let's have coffee, or whatever we have, I don't know what we have.
Professore, vi tiro un po' di paste dal frigo, quelle che abbiamo mangiato,
Sì. Anzi, come si chiama?
È solo quella per la specola, ce l'hanno detto che semplicemente tutte le qualità. Per il resto dalla Cina hanno dato conferma di cultura, però non hanno...
Dobbiamo mandare a sì, preparare la copia del versamento che abbiamo fatto.
Yes.
La donazione che
No,
Philosophically, I could even believe dark matter maybe some form of matter. But dark energy looks really like it's a field.
En su momento Javier, porque ahora
para mostrar eso.
Well, it's extremely exciting because I would like you to live this reality in which we are in a new era, in which we are really checking all our fundamental knowledge changes. Never before we had a situation like that.
turn the slide.
No.
And we should be courageous. I mean, after all, we have discovered since we have, this component of black hole mass. There must be certainly in globular cluster. Maybe in globular cluster. There are so many globular clusters.
For sure.
Yes, in Earth too, but why not in globular cluster?
Maybe according to our theory, maybe only at generate core without failure. Only a core, maybe without failure.
Okay. One when is one.
Yeah.
Fantastic. And let us know.
Okay, thank you. Thank you very much. It's a great honor to show a review of my previous work with all of you. And now I'm a postdoc at the Toronto University. And today I want to show some of my previous work about the detecting dark matter with the multi-messenger observation of supermassive black hole. Okay, sorry. This is my outline. For the marking observations in my talk, I have involved, using the Event Horizon Telescope observation, we use its flux, shadow, and the polarization observed by the Event Horizon Telescope to detect such as wind annihilation around the supermassive black hole. And we also try to finding the axion-like particle, which could induce the oscillation of the polarization oscillation. And then we also try to discuss using the S-star kinematics. We have heard the colors and have several talks today about using this kind of stellar dynamics to detect the spike and the ultralight dark matter around the supermassive black hole. And then I also want to show an example. Okay, we could also, using the primordial black hole, explain the massive galaxy observed by the JWST. And finally, also our previous work, we try to exploring the dark matter distribution around with the nanohertz stochastic gravitational wave background. The motivation why I'm so interested in detecting the dark matter around with the observation of supermassive black hole is, what we all know about the dark matter is about its gravitational effect. Is that if we exclude this effect, gravitational effect, all of it was a subject actually. So following this point, we could know around the supermassive black hole, there will be have far more dense around it comparing to the other regions around in our universe. Okay, this that we could skip. And there is have lots of classical dark matter. Okay, it's classical, not means it's true. Here, from the very ultralight dark matter to the KV and the GV, even for the black hole candle dark matter, they have lots of candidates, and the different kind of candidates, they will have predict different effects. We could detect these kind of dark matter properties with their predictions, such as for the axion or dark photon, it's often for the very light particles, it will shoot like a wave. So it could form structures such as a soliton core around a black hole due to the gravitational bond. Yeah. And it also may affect the polarization observation orbital dynamics and something like also the atom spectrums. I will show later. And for the wings, it could form some like spike, just like you have mentioned from merging dark matter. Yeah, it's similar. Yeah. And also this kind of wing particle, it will annihilation, and this annihilation will affect event horizon telescope shadow. Yeah, we could we could constrain this kind of particle with the shadow of EHT. Yeah, and for the BBH, it will affect. It could add a kind of approach to explain the massive galaxy we have observed in the very high, in the very early universe. Okay, let's move to the first part. It included one shadow and the polarization we have to constrain each. For the event telescope, each has proposed by several years, and each have achieved a lot of results, including the M87 and the Sagittarius A star. We could get lots of information from these two plots, such as we could estimate their black hole mass and the distance to us, and the magnetic field around the supermassive black hole, and also their temperature, flux, polarization, and size, etc. So we could using this information to do lots of gravitational testing or the dark matter, something like that. Here is an example we used. Here we try to searching for the WIMP-induced electron and position radiation around the supermassive black hole. Here, if we didn't consider this term, it's a standard cosmic ray propagation and the radiation function. Here, this is a spatial distribution, and this is the radiative loss, and this is the Softon. For the Softon, we assume is the Softon function is come from the WIMP annihilation. The WIMP around the supermassive black hole, it could decay and become and have an injection to the around the supermassive black hole. And we also consider the injection term. Yeah, it's including the two effects. One is the adventure current, and the other is energy gain. And we could this function was proposed by Robert about 20 years ago. We could solve this function to get the electron and the position propagation equation around the supermassive black hole. Okay, there is also a question for how to describe the distribution of the dark matter around the supermassive black hole. Here we also use something like you have mentioned the spike. Yeah, here is a picture we could show. If we want to describe this place the electron number density with the distance of r and the momentum p, it should included by the larger distance with annihilation particles have fallen down to the black hole. Each will lost due to the magnetic field when the electron close to the black hole, and this when the particle close to the black hole, it will also increase its velocity due to the gravitational potential. Yeah. So each have a balance for the particle. When it's close to the black hole, it will increase their velocity, and it will also lose their energy due to the magnetic field. And
one comment. Yeah. In this statement, you are saying qualitatively, or you calculate with a given magnetic configuration the geodesic and all the motion of each particle, or because this is quite a hard problem, right?
We use this function, and we do the numerical calculation. Yeah. It have included the relativistic effect.
Equation. Can you explain better the equation in colors? Which I don't.
This one.
Yes.
This means one is okay. This is the injection term when we consider the effect of the black hole. Okay, for this one, when the particle close to the black hole, its velocity will increase, but it will losing their energy due to the radius. Yeah. And for this one, maybe you could
Yes.
And for the source term, we used is the Wing spectrum distribution. It's first proposed by Paulo and John Silk about 25 years ago. They have discussed diagrammatic annihilation around the galactic center. Here they use a very simple equation. For the large scale, it's also the NFW square, and for the small one, okay, it should have slope. How to describe this slope? There is one, the radius of the slope, and the slope value. These two values to describe this kind of effect, the effect of the black hole. When we insert, we could get the electron number density with this one. Sorry. With this one, yeah. And with the number density, we could calculate the synchrotron, the electron, the synchrotron emission. Yes. Here is the approach we have shown. If it's only the NFW profile, its synchrotron spectrum is actually very lower. And if we consider the spike, it will about 10 orders larger than the NFW profile. Here is a plot shown for the mass at the 100 GeV and 10 over minus 28 cross section. Their predicted flux from the wings, which were even larger than the total observed by the EHT, because in that plot of the M87, the total flux is about 600 milliamps. Yeah. For this region, it has even larger than four of we have observed. So this region we could say we have excluded these parameters. So we have do the limitation for different WIMP annihilation channels. One is the mu total and the BB and the E plus E minus. And up to now, we still don't have the magnetic field structure at that around the supermassive black hole. So we just use the normal magnetic field. One is 30, and the other is 1. We have excluded this region. It's very interesting. It have included the region at this place, not same with the previous, the Fermilite, AMS, and the CMB parameters. Here is, okay, our result, what we have said, depends on the spike distribution. If we didn't include, sorry, if we didn't include the spike here, its distribution is much lower, and there is almost no constraint.
So you can bring out some spike configuration?
Yeah.
Or maybe 7.
Yes.
Okay.
So here we using the flux observed from the MSD to get the constraint in this region. Okay, the wind predicts the flux even larger than what we observed.
And this, can you compare or say something about the number, the order of magnitude of cross section that you are excluding with respect to some other direct searches?
You're right. Okay.
Because it will always be a sum.
You mean this one? Okay. Here we could see if the cross section is larger here, the spike distribution have annihilation here. We could see this is NFW. Yeah. If the cross section is too larger, then in the plot where it should be lower. This green region is the M87 observed region. About 2.3 shared radius, and the larger is about 4. 7, yeah. And here is, okay, we have, okay, I want to give a more comment about this plot. This is the NFW profile, and this is the red line, just go down without any corners. It will increase directly. And if we consider the wind where annihilation, yeah, when the cross section passing a specific, this one, each will annihilation, yes. And when after each annihilation, they will have injection too, so it will have a balance. Here, so for the density, they'll have a balance as here with length. Here. So we could find the corresponding result as here is when the cross section is larger, and there finally there is no constraint because it seems like the NFW.
But what about the distribution of electrons? You use a distribution of electrons. How should be sensitive to that? Are you using a power law of electrons?
You mean what?
You have in the calculation of the synchrotron, you have a distribution of electrons that as a function of energy.
Yeah,
I suppose you use a power law or something like that.
We didn't use. We used this one. This one. The normal. The normal.
No, but for the electrons. For the electrons.
For the
You annihilate electron positron, and I don't know what happened with the electron positron.
we never tried, but
No, if you go to the first slide, you should have there. Yes. Okay. I got this FE.
the log here.
initial,
Yeah, the log here is really high. I have shown you.
Fe is an electron.
Yeah. Fe is the electron function. Yeah.
No, what I mean is that you have already a distribution of electrons, no? Or you don't, or you are using only electron from the electron positron that you use. That.
Yes, we have
okay.
assumed all of the electron will come from the
annihilation.
yes.
Okay.
Each was a very strong assumption, but it's enough for our make a constraint or make a benchmark for the wind calculation. And then we also try to using the polarization of the supermassive black hole to try to exploring the axion-like particle. This kind of particle was it was predicted from the standard model. Yeah, it will have this kind of scalar field have a mass, and from in the standard model they assume this kind of particle. The axion field could interact with the photon magnetic field, and this interaction will introduce a dispersion in their equation of motion. Here is for the different propagation states. If we have integrated from the observation and the emission point, we could find the delta passage induced by the axiom is also relies on the covering constant and the magnetic field the field, the axiom field amplitude of the observation and emission point. So for the observation point is on the Earth, we can make it's impossible to make change. And for the emission point, it's better. The best way is find a very strong, find a place has a very strong magnetic, has a very strong axion amplitude. Here we both think is the supermassive black hole, especially the Sagittarius A star close to here. But one question is how we to describe the axion around the black hole. Here is some work from the simulation. Okay, they have numerical calculate the Schrödinger equation around the Poisson equation. Yeah, they have get they could get a numerical function to describe this candle, a wave candle particle around the black hole where should likely is one. If it's larger than the Compton radius, we could say it's similar with the
Yes, because the outer part is an FW, so you get a tradition.
yeah. And what is smaller? They think there is a constant because it's smaller than Compton wavelength and the intensity is the same. So when we assume this candle the axion around the black hole is solitary core candle distribution. We could insert the dark matter density inside here, and here is the delta passage, the polarization angle affected by this candle particle, and it depends on the mass and the covering with the photon. So after all this work, the only accessible polarization data about Sagittarius A star is come from the Michael Johnson. They observed the Milky Way center and also get their polarization data. This is their observation result for the date 82 days. Their angle is similar stable and the error is much smaller. So we using this data to comparing the axion predicted results.
Sorry, can I make a question?
Yeah, go ahead.
Do you know any complementary test of the divergence ansatz for the interaction of the boson with the photon? Because this effect should also take place in the early universe and may have a wide effect. So, do you know of any complementary test cosmological of this effect? Because once you have an effect, you have to check in a lot of scales. GRBs, divergences have been checked.
The change of the opacity with the PV emission with 190114C, it has been placed limits for this process. Maybe this plot answers the question. For the lower axiomized, the pulsar will be very sensitive to the axiom. And for the Sagittarius A star we have used, it was placed at here in about 10 over minus 19 and 10 over minus 18. In this picture, it's stronger than the observer and the cast and the other one. It depends on the observation time, actually.
Yeah. I know no constraint from cosmology there.
Actually, they have a constraint from the CMB, but I guess it's in the minus 15, something like that. It's not in this region, that region, yeah. And furthermore, Ivan Cheng and the Xu Jing group, they have using the apple to simulate the polarized emission from the deep pixel by pixel, something like that. They try to get the washout induced by the gravitational by the axiom. So they have made also a constraint from the M87, and they have constrained the uncertainties from the different sides. In this work, we just using we didn't consider the different place. We didn't consider their washout. So they have discussed each more carefully, and they have finished each in Nature Astronomy. If any question for each. If not, I think we could go to the second.
Can I?
Yeah.
So the correlation measurement.
This one.
The previous one. Is that the paper and
This one.
observational result, or is purely theoretical?
Okay, sorry. You mean this slide?
Yeah. I mean, for example, for M87, is it pure calculation, or is actually?
It have included the numerical calculation. They have
No, I was wondering whether it's pure numerical calculation, or is actually contain analysis of the EHT data.
They have included the EHT data in the group. They have included some guide in the Sandori. They have tried to aid the Apple, and I forgot the disk
But that's
model.
simulation, right? Because I don't think EHT has any reliable polarization measurement.
Yes. They get
meter interferometry.
Yes, they get data from their paper, pixel by pixel.
That's untrustable. It's very hard to. Well, one is it's sub-millimeter emission, presumably from dust.
Yeah.
So it has a baryonic induced intrinsic polarization. Two, to properly correlate the signal because the neural matrix is very hard. So I think the ATHT results so far, we can only trust the Stochastic.
Yes, I agree. Yeah. Very good. And for this one, we using the stellar dynamics to constrain the ultralight dark matter and the wing spike. Because in the previous work, we have noticed, the dark matter density around the supermassive black hole is very important for this constraint, right? And they have lots of uncertainty for the density distribution around the supermassive black hole. So it's very important to make it clear what's the situation around the black hole exactly. So here, the direct way to observe, to detect the black hole, the dark matter density around the supermassive black hole is by their stellar dynamics. Here, we have using the CAT data and the part of the VLT data, because after the second time, okay, it should be because it's PDF, so it cannot be. Because when the S2 second passing the closed point of the Sagittarius A star, the gravity never public the data. So we using the CAT data.
Yeah.
It's this one, yeah. You have to show this.
Yes, no italics.
Yeah.
They only have regular.
So we use the data published by their group. When we rebuilt the orbit, the stellar orbit, we need two observations. One is from the point, yeah. The other is from the spectrum. So we could rebuild their position. For the radical velocity, each have also very good measurements. Here we try to using the S2 or some or several stellar dynamics. We using each constraint two models. One is ultralight scalar dark matter. The other is wind. Let me show first one. The ultralight dark matter, okay, is solving Gauss equation around the curve matrix, and for the specific mode is where closing wire efficiency is 0.11 mode. We could make some assumption with in the case of in the S2 case, yeah. Due to the mass coupling in the scalar field under the black hole system, we could say the radius, the gravitational radius comparing to the Compton wavelength of this kind of ultralight dark matter, each was very small. Here we could consider the closed place of the S2 is about 10⁻³ pc, and the largest place is about in the 10⁻² psi. Yeah. For this, for here for the S2 case, this magnitude is about 10⁻³. So we could safely keep the imaginary part, and only considering the oscillation of this of the scalar field. Here is the ultralight scalar distribution we used here, and okay, we introduce the kappa. It describes the cloud. We could say the scalar cloud, comparing to the M scalar and the black hole mice. And the cloud was integration of the dark matter density. Yeah. Besides the gravitational effect, we also considering a very interesting effect in particle community. We named it the frequency shift induced by the interaction of the standard model and the dark matter. Here, classical one is the Higgs boson. They assume the scalar field could interact with the Higgs boson, and it could induce the Higgs vacuum expectation value have a shift. which will affect the electron mass. And finally, will affect our manage the energy shift and then affect the radical velocity we have showed in the previous slides. And there is also could assume interaction between this kind of scalar field and the photon field. Here each will effect alter the fine structure constants like here, and also will affect the energy shift we have showed at here. Yeah, which will make the radical velocity have energy shift due to this kind of interaction. When we considering the two effects, one is the gravitational effect. One is the gravitational mass. The other is the delta V of the energy shift. We then rebuilt the S2 orbit. Due to the measuring errors, up now we could also use the 1.5 post-Newtonian equation. Yeah. Here we insert the we consider the mass included two. One is the point mass. It's from the black hole. The other is extended mass source. The extended mass source is okay for the case one. We consider is a supermassive black hole plus a scalar field, and the other we also include the astrophysical background here. For the astrophysical background, up to now the gravity given the result is about 8 times r over 1.6. This one. There is a slope here for the astronomical background here. So for the mass, okay, it's included a point mass and the extended mass. We added we put the parameter insert to the post-Newtonian equation. We could get okay. Similarly, we do that. Yes, we have a very good conversion counter. But for these two parameters, because it was extended some region, so for the lower one there is no constraint.
Good.
Yes, for these two dark matter parameters, if it was too small, there is no constraint for this kind of dark matter. Here is the fitting result for the case one and the case two. The case two is we have included the astrophysical background. The kappa means the scalar clock comparing to the black hole mass, and the beta is the Higgs coupling constant to the it's the coupling constant to the Higgs. Yeah. So with the best fitting result, we could give extended mass here is about 10 over is smaller than 10 over minus 3. This we could also in astronomy we could say it's the uncertainty actually. But this uncertainty has give a very strong for this kind of dark matter. And also for the coupling, we have our result is much stronger than the Atlas and the supernova result for the Higgs photon and the photon. Yeah. Do you have any question?
Yeah, because you reobtain the constraint from gravity of an extended mass that cannot exceed, I guess, 10 to minus 3 times.
Yeah, solar mass.
So you kind of are in agreement with this statement, but within your scalar field.
Yes, exactly. Yes, it's similar.
But no, my only question is, I don't understand why you solve scalar field around here shouldn't you solve
Structure.
no, the spike? Well, or structure, but why do you consider spike and you consider
The spec is next work.
Ah,
Yeah.
okay.
It's for the ultralight fragmented case.
Ah.
Yeah.
Okay.
Very good.
Not I will move next. Okay, yeah, you have a good question. We could also using the stellar dynamics to exploring the dark matter spike around the supermassive black hole. Yeah, we know the NFW didn't considering the effect of the supermassive black hole. If we consider this black hole in such here, there should have a radius to describe which size each will affect and what the slope will affect. So two parameters, okay, is here. And for this one, it's simpler than the ultralight fragment. We only contain their extended source contributed from the dark matter. Yeah. We just insert this one to the dynamical equation, and we set two types of constraints. One is for the radius, the spike radius, and the other is constraint their slope, which could be more flattened or more steep. Here is, okay, for the S2 case, we have using the VRT data and the CAC data, and give included some region for give some the most limitation for the spike model. The spike model I mentioned here is parameter predicted by Gonzalo and Jean-Pierre. We have give a very strong for the radius and the slope. Yeah. We could say the Gonzalo spike model is disfavored at 1905. Yeah. Thank you. And for the other case, we also considering the we also consider another 4S stars. Yeah, and to be honest, the other stars we included is not changed too much because their answer is very large. I promise. I think you also know this situation. And we also estimate the gravity constraint power for the GNRW and the Inasto spike. It's also a kind of classical distribution in the spike case. And we also considering the dark matter annotation with these kind of things. Yeah. We need to finish.
Yeah.
But oh, okay. Never mind. Actually, I have half of my slides. Okay.
You consider you did some consideration with our organic solution?
No. But I think if you are interested, we could do it in the future. Yeah. This is okay. Today I have listened to you model is very carefully. Yeah, it's also very interesting. Yeah. You have to it very seriously and have a serious paper. But unfortunately, there is lots of paper. They have lots of work about testing the gravity and detect different kind of pragmatic candidates. So I'm using your work.
Okay.
Very good.
Okay. May I just skip my maybe 5 minutes? I didn't. And here we try to using the rapid growing PBH as a seed of the massive black hole. Here, okay, we have observed the JWST have observed lots of massive galaxies, and for the galaxies, okay, here there is an empirical relationship about the galaxies and the black hole. I know they have uncertainty because this function was due with a lower observation. For the high redshift, what we do is introduce the parameters to here, and we have introduced the PBH have a dark matter closed. when we consider the dark matter closed effect, each will have a contribution for their gravitational effect, and will make the acceleration much larger than the naked case. I know for the galaxy community, they didn't care for the dark matter gravitational effect, but it seems not good. So we consider the acceleration and okay, this one. We using this relationship, empirical relationship, try to get their effect and exploring the PBH mass distribution. We know they have hundreds or thousands of PBH models. They have different kinds of mechanisms to predict the PBH. And the different model will have different mass distribution. Here, we both tend to predict. We could use the high redshift observation to constrain or give some information for us to, to know the PBH the PBH distribution. Here is okay. We support the log normal case. And we also considering the as you have mentioned here, and we just add the gravitational effect and environment effect. It will make the energy loss more quickly and affect the spectrum of the gravitational wave we observe. Yeah. Here is some results we have get. So, okay, so we say the dark matter surrounding supermassive black hole spectrum will enhance the gravitational wave background. But also we know when we discuss dark matter, we didn't considering the astrophysics background. It seems not good. And for the calculation of the gravitational wave background, they also didn't consider in the dark matter effect. So the best way is combined together.
Yes.
You are out of time. Yeah, okay. In summary, I have combined two important things. One is observation of supermassive black hole, because in the past 10 years, there have lots of significant observation involved, such as the Inventory Telescope, gravitational wave, JWST, and the post-timing array. Maybe also the gravitational wave, LISA, and the Tianqing, something like that. And there, for dark matter detection, there is also have lots of model to have give lots of predictions, such as for the wings, each will have annihilation, and for the axion, they will have oscillation, and ultralight PBH, they have the effect for the oscillation for this kind of things. And for the supermassive black hole, we could searching for the possible signals of dark matter candidates in the observation of supermassive black hole with the statistical analysis. Yeah, we think our work could shed light on the role of dark matter played in the formation and evolution of supermassive black hole, and offer some fresh physical motivation for future motivation, or right now, actually, it's right now, messenger observation of supermassive black hole. Yeah, thank you.
Thank you.
This has been quite an experience, and you can go back to the first slide.
First slide, okay.
That you showed.
First slide.
The first slide, the first.
This one? Oh.
The second slide, the one where you show. Yes, the one with the M87 versus the ring. I follow you up to here.
This one?
Yes, I follow you up to here. You have put so many things even some scalar field, which I am one of the persons who had idea about that. But I invite you to think about, because I stop at this first slide. I just make you a comment on these first two slides. This is about our galactic center.
Yeah.
That is a very interesting source which we have been dedicated quite a lot of time in this meeting. The other one is another image of the shadow in M87. I have personally to tell you that I have great doubts about the validity of the interpretation of that. You gave an additional one which is based on particle and so forth. But the only thing I would like to stress is that while in this case it's very likely that we see a shadow, in M87 I am very doubtful that we can see a shadow. Maybe they used some special wavelength and so forth, but from the heart of M87 we see one of the biggest possible jet ever observed, extremely energetic, which has nothing to do with that shadow. We had this discussion when this gentleman tried to present this at the Grossman meeting, and they tried to dissuade him. I did not succeed, but he went on and he published this that make a lot of noise in the first page of New York Times and so forth. No, the German guy. Anyway, I'm doubtful. I don't try to follow any theory, especially not this very strange particle that you consider, or even though I cannot see any connection with scalar field and so on. But I stop there because that shadow is an artificial process, because we know that M87 is one of the strongest sources of energy at all sorts of wavelengths, and there is no single shadow on M87. I mean, you can do a trick to take some data, partial data, but if you take all the data from M87, what is clear is that there is a black hole, yes, and a supermassive black hole, but with a lot of activity, not the shadow.
There was indeed a paper very recently showing that what you are saying.
Yes, but there is not one paper, there should be many papers, because this is obvious to any physicist. It's only to the New York Times and to these people that they need something, that they discover the shadow and so forth. This is more recent. This is old, and it's wrong, simply wrong. Everything else you said, I cannot follow. I mean, but I invite you to narrow down your interest and be more attentive, because everything you have put in the presentation, just more modestly look at a source, a point, and work on that. But don't try to do all physics literature and put together in the presentation, because people cannot afford the luxury. This is just a suggestion,
Yes, thank you.
but I hope it will help you. I hope.
So sorry?
I hope it will help you. My
I hope
suggestion.
it will help you.
Yes, thank you.
Okay.
Yes, I see.
Okay, thanks.
No more questions?
I think we have to go.
Yes.
It's late. And I would like to give you a good news. While we are having a shock with order, because we have decided to write an article. And I was relieved because at a given moment during the discussion, the presentation, I had to leave because I had to speak to a person I have a lot of respect. She was my student, and she's still very active. And she's very important for me because was one of my best students. Her name is Nathalie L'Oreal. And when I do something very osé, I want to check with her because we are trying to write a paper with Orge. And she was not shocked by it because, of course, she has been a collaborator with people of the observation. You know, one of the best work on the theory of binary pulsar was done by her and Thibault and Kramer. I mean, it was fantastic work. Before taking the responsibility that we are writing a paper, I wanted to check with her. And she said something, she was not shocked. And she's looking forward to see our paper. But also she said a very nice sentence, very nice, which we should use. In physics, when there is something completely new, you try the first thing which works and publish and even be recognized by this discovery. But now in physics, bit by bit, you start to realize that the situation is much more difficult. And they are coming in different parameters. And therefore, that simple interpretation following that simple, sì, mi dica, sì, fantastico, che bella notizia, non mancherò. Grazie, mi saluti l'avvocato. Well, this is a very important meeting with the lawyer. But excuse me, but this sentence of Natalie is very important.
Can I just add one citation? So Ernest Mach has this famous saying, as the task of physics is not to explain all phenomena, which is impossible, but to explain as many phenomena with as little parameters.
With
As little parameters.
yes.
So it's there's a beauty in
Open Russia.
in
Open is a French philosopher for open
Laser.
racer.
No, This is the thing that Nathalie said is different. This of the Occam things and approach, we also know complain. But what Nathalie said today is a different concept. That when you look at a new phenomenon, okay, you try to explain following, for example, when the paper of the binary pulsar came out, well, you take the Einstein equation, look at the gravitational wave equation, do the plot, and it's clearly you get the Nobel Prize. That is the first point. But what happens in physics, which we are living through, is that as the knowledge amplifies, it's clear that that was a too crude approximation. And there are phenomena equally important that have to be taken into account. And the paper we are trying, it will not come as a shock to you, at least, because we tell you we are going to write the paper, I hope. There is dark matter in the galactic center. A lot we discuss. And we notice that there could be, at the binary pulsar level, a small contribution of dark matter. But the amount of dark matter we discover in the galactic center is 2 months old. We cannot pretend that we have known all the dark matter in the galaxy, because there are also nearby galaxies which they can contribute. And even without galaxies, there could be more dark matter which can contribute. Therefore, we don't have to hurry. We just have to say a paper in which we say that in the limit of, and the reason I want to do this, because the person who characterized us for a long time, you see his picture downstairs on the cellar, is Riccardo Giacconi. Riccardo Giacconi was always very annoyed by the Nobel Prize given for the discovery of gravitational wave. Because it's not, you are not seeing the gravitational wave. In the electromagnetic waves, you are seeing, you are measuring. There was radio between Italy and Canada. I mean, this is no doubt. But the gravitational wave of the Nobel Prize, you have only indirect evidence from the loss of angular momentum. Indirect. And he was very concerned about that. And now we see that if you consider dark matter, there could be other contribution and other source of slowing down. Therefore, Nathalie said, the first try is the simplest. But then, as physics knows more, the real situation comes out, and the reality comes out is much more complex. The reason that I am concerned about all this field is because, of course, we know the result, and this is the law of the binary pulsar. And that's this problem, which we are going to evidence. But the other two cases, we know they are fake. We know they are fake, and in period, there's no possibility. Therefore, this is the a very dramatic situation in physics, that you have two experiments not correct, and you have one experiment which was perfectly okay with the data when they were published and feed. But now we see that the situation is much more complicated because there can be contribution of dark matter. And I think with the due nobility, we have to point out a paper on this, if you agree. With the new nobility, without entering into considerations. But I think it's a fantastic case. It's a fantastic. I hope you go to the point. As you go on, physics comes in with new data. And this is fantastic. This is what we are having this meeting, because they were the pulsar. Okay, we understand everything. A pulsar, pa, 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 pa. We have then the gamma ray burst comes. Careful, because yes, you have the pulsar, but it comes with something else. And now we are able to, if we work enough in these days, we can also tell that in a gamma ray burst, there is one of few objects. We have the theory, but we did not show it yet. But there is one of few sources. But this is the beauty, that you change completely you are following one view, you are changing completely the point of view, because physics come out, and we have to be ready to modify whatever is needed. Okay, enough for tonight. Right.